Hello there. In this video, we're going to do a queue tutorial where we want to set custom server priorities. And we've done that in previous videos, or at least in one previous video. But in this video, we're going to make sure that it's also that the priority for a given server depends on the individual as well. That can be appropriate when you're trying to model things where a specific server has expertise that other servers don't have. And so if they're trying to serve a particular customer or patient, if we're thinking healthcare, where specialization happens a lot, that this is a way, it's not the only way, but this is one of the ways that you can do that with the QPython package. So let's jump into the implementation. At the top, of course, we're importing the Q library. And here we're defining our custom server priority. The general type signature here is that it needs to take a server and it needs to take an individual. And it's going to return an integer, or it might in general be an ordered type, but I know that definitely integer is enough. So for any countable set of priorities, you can map them to integers, and that should be fine. This implementation, by the way, comes from the Python or the QPython documentation. I'm not sure that this is how I would exactly implement it, but and I've added some minor stylistic things, but here we've got basically a sequence of if statements and returns. So what we've got here is we've got if individual.customerClass is class 00. So in Q, you can have these things called customer classes, and by default, a simple way to name them is class 0, 1, 2, whatever, but you could name them almost anything else, and I think I'd have to double check, but it may just be sufficient that they are hashable. I'm not sure what other constraints. Certainly strings work, but I know I've used non-strings in the past for this type of thing. So if the class is 0, and for whatever reason we're defining the priorities here, that it's a mapping of 0, 1, meaning the first server gets a priority of 0, second server gets a priority of 2, and the third server gets a priority of 1. And then we return, based on the server ID, the priority. If the individual customer class is number 1, then we have a slightly different set of priorities of 2, 0, 1 instead of 0, 2, 1. Okay, and then we return that priority based on that server ID number. And mostly just to keep the type system happy, I return 0 if it somehow passes through all of these cases. But you may, depending on your implementation, you might actually want to throw an error here if you've only got 2 classes and there shouldn't be anything more. An error is one way to basically catch it at the end. Anyway, so as is the case with Q, we have to define a network. So we've got our Q network, and here we're using the create network function. And we will construct some arrival distributions. Here we're keeping it really simple because we don't need to get too much into the reads of all the features all at once. So we've got a couple of classes, class 0, class 1. These need to match with these ones up here. They do, class 0, class 1. And here we've just got exponential distributions of 1 for the arrival time, inter-arrival time distributions, and for the service time distributions for how long it takes for a service to complete, they're both exponential 2. There are 3 servers here in this system, and hence that is also coupled to the priorities that you've got. There needs to be priorities for 3 of them. You could do like a get method on a dictionary to basically fill in defaults if you wanted a default priority. Okay, and then you actually have to pass in the server priority functions. Now, while we have 2 different classes in this network, we actually only have 1 node. So we've only got 1 custom server priority. You provide 1 of these for each of the nodes. Okay, so if we want to run a little simulation here based on this definition, this network definition, we can go if dunderName is equal to dunderMain, just for our main program, and set the seed to whatever you like. Here I went with 2025, which I think is different than the documentation, but I don't care. So then we initialize a simulation object, and we pass in our network that we defined above. And then we run the simulation, in this case, until a maximum amount of time of 1,000 units of time on whatever unit scale you wanted to think about time. And for the sake of showing something related to the results of this, we're printing the utilization for each server in the first node. This system only has 1 node. If you had multiple nodes, you'd loop over the nodes. and you're accessing this servers thing, although the type system is not sure that that exists. It will exist in Q. So what can we do next? We can run this thing. So let's go Python prioritizing using the individual, and there are our utilizations for the different priorities. Now, really, because we put symmetries in of, and what I mean by symmetries here is really we've got the same arrival time distributions. So knowing that maybe some classes are more directed towards specific servers than others, equal arrival rates, you're going to get kind of a, it's not an equal mixture, because I think in both cases, yeah, we've got the third server is mapped to 1 in both systems, and that's why when we see the utilization over here, it's only 0.23, whereas the other ones get closer to a third each, more than a third, technically, just because of how stuff adds up. So let's maybe tinker with this a little bit to show that this distribution for the utilizations can change too, depending on the inter-arrival times. Let's set this to a whopping 10. So that's a very high rate, means we should expect a lot more of class 1, which means that the class, that the prioritization for the servers that are higher priority for class 0 are going to be busier, we expect. But there you can get saturation effects, so I'm not entirely sure what will come about from this experiment, but I'm expecting that the first utilization for server 1 will be higher. Let's take a look. Yeah, no. We basically just flooded the system. Sorry, it wasn't a great example. It was worth a shot, though. Let's put this to something a little bit more modest, because if you saturate, I think it's gonna just, yeah, that's a little bit more like it. There's gonna be some, of course, sampling variability. Oh yeah, I'm setting the seed, so there won't be. But now let's turn off the seed just to take a quick look here. Why not? Let's just, I'll comment it out, actually. So now we should see some more sampling variation, and actually, pretty stably, this is what we're getting. So I made a mistake earlier of just setting the rate for the class 0 arrivals so high that the priorities didn't really matter. I was just flooding the system. But you should be able to see some differences when, yeah, you should be able to see some differences when the rates are relatively different, but you're not completely saturating things. Okay, so, yeah. That's the gist of that. I'm not sure what else I want to talk about in this video. That's probably good for this video, but the real key takeaway, just to summarize, is to say that these custom server priority functions, I mean, they can really take the server and the individual. You can make use of both, and I think as we've talked about in earlier videos, the individual instance that is going to be passed also indirectly has references to pretty much everything else in the state, because you get a reference to the simulation itself. The simulation has references to all the nodes, and the nodes contain the various things that you might want access to. So it really is a bit of a powerful way of getting access to full state. To some extent, I kind of wonder why the design doesn't just point to something like taking in the simulation state or something. But hey, I mean, I can't speak to the general reason for this. Anyway, hopefully that's helpful for you in building simulations in which the priorities actually depend on properties of both the server and the individual for who serves whom. With that, I wish you a good day and enjoy Q simulating.